fun, y'all. Have fun, y'all. The city breathing all down your neck. Bad news and good dope special effects. And reality's teeth, bright, black, sinking in deep. Ow. Who ain't shy of the pain? Who ain't shy of the pleasure, just the same? Life is a game, I heard the homies say. Well, I came to win, so I'm not here to play. Have fun, get it, get it, get it, get it, get it. Yeah, hey, get it, get it. Yo, don't stop. Ecstatic, get it, fantastic, get it, wow, get it, wow, get it. People. Bad news and good dope, powder, potion, pill, smoke. Baby, how you trying to go? Duro or dulce, fast or slow? Yay, no, it's okay, you can have it your way. Nah, it ain't all good, but baby, I'm cool. Feeling great, feeling good, how are you? 10% condition, 90% response. Survival mathematics, the number man song. Old dad dropped the jewels so pure. When the times get raw, it's something I recall. Sometime I don't remember it at all. And I get stormed by the weather, but no umbrella. Sky release pressure and the ground get wetter. My outfit effed up, I could've looked fresher. But guess what? The hell with parade day rain. Tsunami of sunshine, the bomb is just the same. Life is a game, I heard the homies say, but I came to win. Dante, get it, play, get it, get it. Brooklyn, get it. Ecstatic, A-Day, Speedball. Bad news and good dope, powder, potion, pill, smoke. Baby, how you trying to go? Duro or dulce, fast or slow? Yay, no, it's okay, you can have it your way. Nah, now's the time, but baby, I'm cool. Feeling great, feeling good, feeling good, feeling good, feeling good, feeling good, feeling good. Ha. Every day, every day, having a good time, every day. Ha. Having a good time every day. Having a good time every day. That's cool.
All right, so we started looking at trees last time, and that's what we'll be doing for the rest of the semester here. Just to review really quickly here, a graph, more generally, is a collection of nodes or vertices and edges connecting pairs of those nodes. But a tree is a connected acyclic graph. We say that it's connected because if you can get from any one node to any other node by exactly one path. If you can't get from one node to another node, that means you've got a disconnected tree. And you can look at those, but they're called forests. Right? We're only going to be looking at trees. It's acyclic in that it has no cycles. Right? Now we're talking about simple cycles. So it's not like you can go from A to B to C, back to B to back to A. Right? That's not a simple cycle because it traverses the same edges multiple times. Instead, a tree has no cycles. Remember that the length of a path or a cycle is the number of edges on it. And we made two observations immediately, that in a tree with n vertices, there are exactly n minus 1 edges. Right? Any edge that you add would induce a cycle. It would automatically create a cycle. Right? The removal of any edge will immediately disconnect the tree and cause it to become a forest. And so that's why we say that if it has n vertices, then n minus 1 edges. And then another observation that we made is that in a tree, between any two nodes, there is exactly one path between them. If there were multiple paths, right, if you had a node here and a node here, and there's one path here and one path here, what does that do? Gives you a cycle. If there were no paths between them, then that gives you a forest. And so consequently, there is exactly one path, right? That's a lot of structure, okay? Now what we're going to do is we're going to give it even more structure. Let me go ahead and jump over here to my tree. Nope, not databases, trees, and I want that one right there. All right. All right. Now remember that I asked you to imagine that you could reach into the screen and grab onto any one node and pull it out and then dangle it, right? And you would end up with, say, if it were A, right, then you would end up with D, E, and F hanging off of it, D, E, and F. Now, why did I write it D, E, and F left to right like that when over here it was F, D, and E? Right? It's because we're using our trees to store data. We want our data to make sense. Data is written top to bottom, left to right. That's why we are orienting this top to bottom and then left to right. Right? And that's, make sure that this is working. Uh-oh. It was working before. Just a second. Okay. Transition. All right, hopefully that fixes it. Let me keep these on, make sure that it works still. All right, so, okay, there. All right, that seems like it's working now. Nobody's watching though. It claims that there's one person watching. 4 people are watching, but not bringing any attention to the fact that the sound's not working. In any case, again, we're orienting this top to bottom, left to right. Off of D, there is nothing hanging any further. Off of C, however, F and G, or sorry, not F, but oh wait, did I write this wrong? D, E, F, right? There we go. Off of D, E, F, that's not C right there. Off of E, nothing is hanging off, and then off of F, we have C, G, and then finally B hanging off of it. Because what you do is you grab it out of the screen, you dangle it, and you let the gravity take over for you. Right? Well, that was just A. Right? If you had grabbed it by something else, say F, you would have a different topology. You'd have a different looking tree. Off of F is hanging A and C. Right? Off of A is hanging E and D, or D and E if I write it left to right. Right? Hanging off of those two is nothing. But hanging off of C is another G, and then B. It's the same exact tree, just with a different orientation. That orientation is going to be read top to bottom, left to right. Right? And so, again, trees can be oriented top to bottom, left to right. At the very top, we have what's called a root node. Right? Any node with 0 children is called a leaf node. Leaf, right? Leaf, there we go. All other nodes are internal nodes. Internal nodes, okay? Let's look at a fuller example here where it is actually oriented. All right, so let's go ahead and grab trees, and there we go. All right, there. So up here, A is our root node. And if I highlight all of the leaves, a leaf is something where there are no children here at all. Right? Now, if I were to take this and reorient it by pulling one of these out and then dangling it in a different direction, some of the leaves would change, right? Obviously. But as it is, as it's presented, anything with no children is a leaf. What about F here? F has both children, or it has 2 children, excuse me. Otherwise, these are the leaf nodes that I've highlighted. Leaf nodes. Right? All other nodes are going to be internal nodes. So if you want those highlighted in a different color here, this is an internal node. All of these are going to be internal nodes right here. The root node is special. It's different. Right? It's all by itself there. Okay? So we've got leaf nodes, internal nodes, and the root node. Now, this induces a parent-child relationship. Right? Let's come over here. Right? Where you've got a parent, you've got children, you've also got ancestors, you've got descendants. You can talk about siblings, right? If they're all children of the same parent, then those are all the siblings. You can talk about cousins and aunts and uncles. You can use all of that familial nomenclature to describe a binary, a tree, oriented tree like this. Right? But what I want to do is I want to add even more structure to this. Right? The structure that I'm going to add is I'm going to impose a restriction. We are going to limit the number of children that anybody can have to 2 children. You can still have no child and you still be a leaf. You can have 1 child or 2 children. And because I'm orienting it left to right, you can have neither children, neither. Right? You can have a left child. You can have a right child, or you can have both. No matter what, it's going to be limited by 2. Right? This is known as a binary tree. Why is it a binary tree? Because it's base 2, right? We're limiting it to 2 children here. You can talk about ternary trees, quaternary trees, quintenary trees if you want, or you can talk about more generic trees with k children, right? We're not going to do that though. We're going to restrict it to binary trees. By the way, what would happen if you restricted it to 1 child? What would a tree where you've got an orientation here, and then there's a child, maybe a right child, maybe a left child, and another left child, another child, another child, another child. Right. What does that look like to you? If I were to take it and stretch it out, it's a linked list, right? So this is a little bit different than a linked list in that we're going to have potentially multiple children. Verify yourself that this is indeed a binary tree. Right? We have A with both a left child and a right child. We have E with no left child, but it has a right child. We have, what's the other example? We have M with a left child, but no right child. And then we also, of course, have the leaf nodes with no children at all. Right? Now, this is not a full tree. Because there's no left child here, there could potentially be an entire subtree hanging off of that thing. But it's not there because it's been trimmed out. Right? And you can talk about pruning the tree or trimming the tree or cutting the tree or even grafting the tree. If you want to take this and graft it on over there. Right? So all the terminology that you could have as an arborist or a family tree, you can also use in this stuff. Right? Arborists are those who take care of trees, right? I think right, there's some, I don't know exactly what they do, and there's a couple of other terms to deal with trees, but whatever. Arborist, Arbor Day Foundation, right? All right, so that's a binary tree. Let's look at some more terminology here in the context of trees. Right? The depth of a node, right? The depth of a node, U, is the length of the unique path from the root to U. Now remember, I am safe in calling it the unique path. Why? Because we're dealing with trees. There is exactly one path from any one node, the root, down to any other node. Right? And so there's exactly one path, and it's unique. Let's go ahead and start listing out nodes here. Oops. Node. And its depth. A, we'll come back to that. B, C, D, E, F, G. Right? So what is the depth of B here? Well, the depth is the length of the unique path from the root node down to B. So it's going to have a depth of 1. Likewise, C is also going to have a depth of 1. Tell me about D, E, and F. Because I drew them all on the same level, right? 1, 2, 1, 2, 1, 2. They're all going to have depth 2. Right? All of these. Right? What about G, H, I, J, and K? These are all going to have a common depth as well. 1, 2, 3. 1, 2, 3. 1, 2, 3. Right? These are all going to be depth 3. Depth 4 nodes, L through Q, are going to have depth 4. What about R? 1, 2, 3, 4, 5. It has a depth 5. Right? That's the depth of the tree. The depth of T is going to be 5 as well. The depth of a tree is the maximal depth of any node in that tree. Right? So the depth of the tree itself is the maximal depth of any node. What about the depth of the root? Right? Yeah, 0 by convention. Why? Well, it just works out that way, right? Deeper nodes have a larger depth, right? And you're going from 5, 4, 3, 2, 1. Well, what's left? 0. It also makes sense because what is the length of the path from A to itself? 0. You just stay there. Don't go anywhere. Okay? All right. So how can we exploit this structure? Right. Suppose that you have a full tree, a full binary tree, and every node was present up to on every level up to the maximal depth of the tree. This one is clearly not a full tree, right? There should be an entire tree hanging off of this thing right here. There should be an entire tree hanging off of this thing. There should be an even bigger tree hanging off of this thing. So let's instead start building our tree from a single node here. Right? And let's go ahead and note the depth, 0, and the number of nodes at that depth, 1 node right there. By the way, several years ago, somebody proposed, I've never seen it in the literature, but some student proposed that we call this a seed. And I like that, so call that a seed. Right? A single node tree. Right? All right. What if I went down to depth 1? Remember, it's full, so every child exists. And so there are 2 nodes at that level. Okay? What about the next level? 1, 2, 3, 4. Right? What about that next level? 8, 3, ... What's the pattern here? What if I told you at depth k, how many nodes are there going to be? 2 to the power of k, because this is a geometric sequence. 1, 2, 4, 8, right? We're going up by powers of 2. What if we went all the way down to the depth of the tree, the maximal depth of the tree? At that level, it would be 2 to the d. But now what I want you to do is I want you to sum all these up. So the sum of k running from 0 up to d of 2 to the k. Again, this is 1 plus 2 plus 4 plus 8 plus 16 plus ... 2 to the d. That is not little old Gauss, right? This is a geometric series. Right? So what's the closed form solution of this? Generally, what is it? K is equal to 0 up to d of x to the k. Do you know what the general form is? It's x to the d plus 1 minus 1 all over x minus 1. Something like that. Don't quote me on that, but whatever it is. For 2, it's just simply going to be 2 to the d plus 1 minus 1. Okay? Let's verify that. Let's come back over here. What if we restricted ourselves to this subtree right here? Then the depth here is going to be 3. And so the summation of k running from 0 up to 3 of 2 to the k is 1 plus 2 plus 4 plus 8, just as I wrote over on the side, 15. Is that equal to, question mark, 2 to the third plus 1 minus 1? Well, that's 2 to the fourth, which is 16 minus 1. Verified. Okay. All right. Well, how does that help me? Remember that n is the number of nodes, the total number of nodes. And that I have that n is equal to 2 to the d plus 1 minus 1. And that d is the depth of my tree t. Okay? How does this help? If we can develop an algorithm or a series of algorithms so that we can insert, retrieve, and delete elements from a binary tree such that all operations are proportional to the depth, and we can guarantee that the depth is small, then we've achieved our goal. Remember, the whole goal here was, well, we want efficient retrieval, search, insertion, and deletion. Linked lists were efficient if you did one thing, inefficient if you did another, and then it was just reversed on array-based lists. Right? Stacks and queues were always efficient, but they restricted your access to do so. What we want is a general purpose data structure that we can do all 4 of these CRUD things, create, retrieve, update, and destroy. And if it's proportional to the depth and we can guarantee that the depth is small, then we've achieved our goal. With a full binary tree, we have that guarantee. what is the depth here? In other words, solve for d. N plus 1 is equal to 2 to the d plus 1. How do I solve for d now? Log base 2 of n plus 1 minus 1 is equal to d. In other words, d in a full binary tree is going to be order what? Log n. Right? Exactly the same as binary search. And it kind of makes sense here. Right? Let me go ahead and clean this up a little bit first. Right? How does binary search work? It looks in the middle and says, okay, that's the thing that you're looking for, or it goes to the left to search that way, or it goes to the right to search that way. If this were a full tree, what have I effectively done? I've cut it in half. Right? Going over here, I've cut it in half again. Going over here, I've cut it in half again. You're always cutting it in half if it's full. Now, of course, this one's not full, and we don't have that guarantee necessarily. We'll get there almost in this course, but not just yet. Right? So again, a full or nearly full binary search tree has a guarantee on its depth. If you can perform operations proportional to the depth, the operations will all be efficient, order log n. Right? It's not going to be this one's efficient, but this one's not, and then vice versa. They're all going to be efficient. Okay. Before we do that, though, let's start doing some practical stuff. How would we actually implement this in Java? Right. Let me come over here. I've got a brand new package here. The first thing that I'm going to do is I'm going to create a node. Just like I did with linked lists, we had a node, right? I'm going to call it a tree node, though. And I'm going to immediately parameterize it because I already learned my lesson that I should be parameterizing everything. So I write one tree implementation, and it can hold whatever data you want. Strings, integers, doubles, whatever. T's. Well, it's going to hold an element of type T, private, final, T element, right? All right? And it's going to have other things. One tree node here. Focus on this one tree node here. What is it going to have? A left child and a right child. And a parent. Good. Because if you traverse down, wouldn't it be nice to be able to traverse back up? Did we learn our lesson with a linked list? That going one way was nice, but going the other way was just as nice, right? And more convenient. Right? So I'm going to keep track of those tree nodes. Private, tree node, node, T, parent, right? Left child and right child. Left child and right child. There we go. All right. Let's go ahead and generate a constructor. Where is constructor? I'm going to do it just with the element, because just like I did with the linked list, I'll go ahead and put that item in the linked list, but what about the next? What about the previous? I don't know yet. I don't know the topology of this. I'll let you set those later on. Okay? Okay. Let's go ahead and also generate getters and setters. In fact, I'm going to select all the getters, select all the setters. Come on. I want them all. Select all. There we go. Right. And generate. Most of these make sense. Get parent, set parent. Get left, set left. Get right, set right. Get element. Why don't we have a set element here? What was my design choice at the very beginning? Making it final. Once you create this node and put the data in it, that's it. I'm not going to let you change the data. Because I'll let you take this node and it's already part of, I'll let you prune it from the tree and then maybe graft it on somewhere else. I'll let you change its left child, right child, get the parent, get the left child, get the right child, do whatever you want, except do not change this data. Right? That's one choice. Right? I could have said, okay, go ahead and change the data all you want. Right? I like being as conservative as possible with these changes. Right? What else might be convenient with just the node? Okay, toString, public string, toString. Yeah. This dot, I don't know, element, return this dot element, and then we'll explicitly go toString there, right? Something like that. In other words, I'm only going to print the data inside that. If you want to, we could go ahead and say print everything. string dot format, right? And here's the node percent %s with parent percent %s, percent %s, percent %s. Right? Parent, left child, right child. I don't know. Format it in some way to make it make sense. So this dot element, this dot parent, this dot left, this dot right. You do have to be careful there though, because you might end up with an infinite recursion here, right? If I print my parent is going to print me, right? In fact, there's an old nice. I always like to bring this up. I think it was a poem. It's a riddle. It's a riddle. That's right. Right. So there's this guy, and he comes up to this painting, and there's somebody in the painting, and he goes, "I recognize this person." Right. And brothers and sisters, I have none, but this man's father is my father's son. Who am I? Who's in the painting? So brothers and sisters, I have none. So there's the guy, no brothers, no sisters. But this man's father, right, is my father's son. Who is it? It's a painting of himself, right? He's looking in a mirror, right? So it's just a little riddle. How is that relevant over here? Well, if I print my parent, what is my parent going to do? Print me, right? If my parent prints me, what am I going to do? Print my parent, right? So maybe I'll stop this entirely and say this dot parent dot element, right? Not the entire node, but the element at that node. Right? There we go. All right, there we go. I like that. Return that. Okay. Anything else? What were some of the definitions that we went through? What is A? A is A? Root? So wouldn't it be nice to know, are you a root or not? Public, Boolean, is root. Am I a root? How do I know if I'm a root? My parent is null. Return this dot parent is equal to null. Right? If my parent is null, then I am the root. Right? What about the opposite? What's down at the bottom? Public Boolean is leaf. Right? Okay. How do I determine that? Let's look at this example. The depth of P is 4, but the depth of R is 5, but they're both leaves. Right? In fact, I could have a leaf way up here too. Right?
They have no children.
No children. So is leaf, I have no left child, I have no right child. Those in and of themselves seem like they're convenient functions to have, right? Get left, get right. Well, what about public Boolean has left child? Right? Public Boolean has right child. Right? That return this dot left child is not equal to null. Because if you have the child, then it's not null. And this will end up being the right child. Okay. All right. Then I could call those two other functions, but something that's even more convenient. Right? I don't care if you have a left child or right child. I just want to know how many children do you have. Public int get num children. Right? Let's go ahead and create a variable here. Value is equal to 0. Right? If this has a left child, then I'll say value plus plus. If this has a right child, then I'll also say value plus plus. Right? And then I'll return the value. Okay? Now how can we easily answer this question, because I've already done the grunt work up there. This dot get num children is equal to 0. Right? If you don't have any children. Right? Otherwise, it would have been like a complex series of, well, do I have, my left child is not equal to null and my right child is not equal to null, or whatever, and then complicated logic's not that complicated, but I like dealing with, breaking it down, because these things are even more convenient. Eventually, we might have need of all of these things, right? That's just one node. What does the entire tree look like? Binary tree, T. I'm going to keep track of all the nodes. Private list of tree node holding elements of type T. All the nodes. Right. Should I keep track of every single node? That seems wrong because, well, that's just a list, right? Why are we doing trees to begin with if you just want a list, right? Instead, I'm going to keep track of one node. So should I just keep track of some random node in the middle? Some leaf node? No, there are many of those. What's unique in this tree? The root. That's where everything starts. From the root, I can get to anything else by traversing down to the left, or I can traverse down to the right. Right. So I'm going to keep track of only the root. Private tree node T root. Okay. Public binary tree. This dot root is equal to null. Right. I may eventually also want to keep track of the number of nodes because that seemed convenient with lists too. Private int size. Right. So this dot size is equal to 0. That's an empty tree. By the way, let's look at another corner case example here. That is a tree of depth 1. A seed, as we said, is of depth 0. So what is an empty tree? Here, I'll just draw the empty set there. What's its depth? Null, undefined, or if you want to use this convention of going backwards, 0, 1, 0, it'd be -1. In fact, that is defined in a couple of data structures and algorithms. The height, balance factors, stuff like that, you also can talk about negative values. Right? So an empty tree would be of depth or of height -1. Okay. So what's my depth and my height here? I don't know. I'm not even going to do that yet. Right? But my size is most definitely 0. How do I get stuff into this tree? How do I get stuff out of this tree? How do I find stuff in this tree? So let's come back over here to this picture. And let's clean this up. Okay. So what I want to do is I want to search. Right? I'm going to hold off on answering how to get stuff into the tree later on. I'm going to start with one that's already built. And I'm going to want to know how to get things out of the tree. I want to search for the data in I, right? In the node I. No, sorry, let's go with J. J. There we go. There's J. I was able to find it because I was able to see the entire picture. Right? Can a computer with only access to the root here see the entire picture? No. It is only local information. Right? I'm right here. Right? Here's me, the dumb computer, standing on this node right now. Okay. Where do I need to go to find I? Should I go this way? Should I go that way? Right? How, obviously, a human is able to see that it's down here. But this guy right here, standing only with local information, doesn't know which way to go. So here's a really, really old trick. Do you know the left or the right-hand rule for solving a maze? So you're in a maze, pitch black, you can't see anything. Assume that there's no pits that you'll fall in, no dangers or enemies or anything like that. How do you get out? Right? Left hand on the wall, just walk forward. That's it. Right? Eventually, you will eventually traverse the entire maze. Might end up traversing the entire maze, but you will get out eventually, as long as you are consistently holding onto that wall. Because if you go down a dead end, that dead end comes back out, right? And you continue on for the rest of the maze. It might take you a while, but that's how you solve it. This guy is going to take his left hand and he's going to put it on the wall of this tree right here. and we're going to walk around the tree. So let me clean this up. We're going to walk around this tree, detecting whether or not that's the thing that we were looking for. When we get down to our dead end here, we start traversing back up to its parent. And then there's another corridor down there. So we're going to go ahead and go down that way, go down that way. We end up coming back, and you now start to see the pattern that you're traversing around the perimeter of this tree. Eventually, you will hit every single node. Right? Eventually, when you get over here to J, oh, I found what I'm looking for. Stop. Right? That's the thing. That's the guy that you're looking for. Unfortunately, you did go down the wrong direction, but them's the breaks. Right? Until we add more structure to this to avoid that. Okay? We're going to do this in one of three ways. We're either going to do this in a pre-order traversal, an in-order traversal, or a post-order traversal. It's the same traversal, it's just how do you process the nodes? So let me move this down. So node processing order. What I'm going to do is I'm going to look at this locally. Look at the root node, its left child if it has one, and its right child if it has one. Okay? Now, you could go ahead and process this node immediately. Just look at this. Is this the guy that I'm looking for? If so, no need to continue down the left or the right. Right? Done. You found it. So, you process the root node first. You still, if that's not the guy that you're looking for, then you still need to go down to the left subtree and to the right subtree. We'll do it in that order. Left and then right. Or you could say, well, I don't know if that's the guy that I'm looking for. I want to go ahead and go down left first here. And so I'll go down, explore the entire left subtree first. When I come back up after from traversing around the perimeter, then I'll process the node. So I'll go ahead and do the left subtree first, then the root, and then go on to the right subtree if necessary. As you can see the pattern here, the post-order traversal is going to do the left subtree first, then the right subtree, and then finally the root. Now you might be asking yourself, well, wait a second. I see three things here. 1, 2, 3. How many permutations are there of three things? 3 factorial is 6. That's half of them. Where are the other 3? All they are in reverse. You go right, left, root. Right, root, left. Root, right, left. In other words, you go right first. That's not how we read, though. We read left to right. And by the way, you could just take this and then reverse the 2 nodes there, and you would get the same thing. Right? So we're not going to bother going right and then left. We're always just going to go left. Okay? What would it look like on a very small tree here? Let me go ahead and go A, B, C, D, E, F. There's a very small tree. Let's look at a post-order traversal. Right? Now, a post-order traversal is going to start at the root. All 3 of these are going to start at the root. It's going to do it in a root, then left, then right manner. So the very first one that I look at in a post-order traversal is going to be A. Right? Then I go down and I process the left subtree. Look at this as if it were one tree. Right? B, D, and E. Now it becomes really easy because you just go root, left, right. And in that order, it's going to be B, then D, then E. So B, D, E. I don't need that hyphen there. Right. At this point, I've done the entire left subtree. Remember, I already did this root here, and I've done the entire left subtree. It's done. Now I go to the right subtree. I process C next. And then I process its left tree. But is there anything there? Nope. So nothing to process. And then I process the right subtree, F. Okay? Just a single node tree. Oh, sorry, what did I say? Post-order traversal. Pre-order traversal. Right. and then an in-order traversal. These are all one words, by the way. They're not two words. There we go. All right. So a in-order traversal is going to do the entire left subtree before it does this root node, and then it does this over here. So 1, 2, 3. Right. So it doesn't immediately produce or process A. Instead, it goes down to the left subtree. Now I'm looking at this left subtree here. I don't immediately process B. Instead, I do the left, then I do B, then I do E. 1, 2, 3. So D, B, E. Immediately you see that it's definitely not the same order, right? Not the same enumeration. Once I've done the entire left subtree, now I do A. Right? Then I do the left subtree. Right? I do not process this first. Instead, I go down to the left subtree, but that's empty. So then I end up processing C and F. An in-order traversal. Tell me where the root is. It's right in the middle, median. Those words have no meaning here, right? But everything in the left subtree is over here. Everything in the right subtree is over here. Versus pre-order traversal, the root is always the first. The root is always the middle. Tell me about a post-order traversal. Immediately, where can you tell me that A is going to be? All the way at the end. Let's do it though. So post-order traversal, I'm going to go left, then I'm going to go right, then I'm going to do the root node here. Looking at the left subtree here, I do the left, then right, then the root. So D, E, B. Oops. D, E, B. The first three nodes for all three of them in the enumerations were all different. Okay? I'm not going to do A here because I have to do the right subtree first. So I look at this right subtree. I'm going to do the left, but that doesn't exist. Then the right, F, and then the root. So F, C. And then finally, once I'm done with both the left subtree and the right subtree, only then do I process the middle or the root node there. Right? Three unique ways of doing this. Each one of these, by the way, has their own applications that we'll talk about later. So all three of them are necessary. Right? They're all the same order in that you are, traversing down as deep as possible and then coming back up using this left-hand rule, this perimeter traversal. But the order in which you do it changes, and that gives you different applications. Okay? In fact, let's do this one with the rest of our time today here. You're going to help me out here. In fact, I don't know. Experiments in active learning if you want to. Do you want to do it? Right? By yourself? Like at your desks, I mean, with the people sitting next to you. This is that active learning thing that everybody's always been trying to do, right? I'm going to let you do it, right? I'm going to do it up here. In fact, I'm going to do. We have like 10 minutes left. I'll give you 5 minutes to do it, and then I'm just going to do it really, really quick up here. So, go ahead, work. It's going to suck for the live stream, but oh well. You do it at home on the live stream. All right, so you finished the pre-order for me. Did I do it right? Or did I miss something? I think I did it right. C, F, J, P, Q, K. Good. With pre-order traversal, all you have to do is run down, run down, run down. All right, so if you've got a nice run like that, you could always run down there. Right? What about in-order traversal? So I got you started there, right? We go all the way down over here and then do this because there's no left child. So we do this and then there's no right child. We come back up there, do G, then we go M, but we hold off on M until we've done the left child here first. Then M, and then the right child, but we're done with that. Right? There's nothing there. All done there. So now we do D, right? Then there's nothing there, so H, N, D, H, N. And now we're done with this entire left subtree, so B. Oops. Then what? E. We don't do I next, we do O and then I. Right. Why? Because we do the left child first, then the root, and then the right, but there's nothing there. Only after we're done with all that, now we do A. Now we can do this left subtree here. There is no left subtree here, so we do C. Then what's next? P, J, Q. Then F, then K. What about a post-order traversal? I got you started there as well. Left, then we go to the right subtree here, but we do the left first. Then we do the right, but there's nothing there, so we do M last and then G. Where do we go from there? Not D, instead we do this tree here first. So we do this one, then this one, then this one. So N, H, D. N, H, D. Right? Then what? O, I, E. Then B. We don't do A because even though we've done this entire left subtree here, we need to do this subtree and then we'll do A. Remember, it's always at the end. Right? So speed run this. What is it? It's going to be P, Q, then what? J. It's root, and then what? K, F, C, A. There we go. There we go. So there is pre-order, in-order, and post-order. How do we go about implementing those? We'll start there next time.